All right, what's up, people? This little video is going to be on something called intermolecular forces. There's another video on intramolecular forces, but this video is on intermolecular forces. Intermolecular forces hold two different molecules together. So let's write that down. Intermolecular forces hold two different molecules together. All right? That's what they do. They hold two different molecules together. Let's take a look at this. There are several types. There's three types that we're going to talk about of intermolecular forces. And the first intermolecular forces we're going to talk about are called London dispersion forces. And they're very, very weak. They're the weakest ones. Let's think about propane gas. Have you ever felt a propane gas canister? Inside of that canister is a liquid. You can hear it sloshing around. That's because we put the propane under so much pressure that we've turned it into a liquid. Well, how did we do that? London dispersion forces. Here we go. This is a molecule. Let's think of somebody that could be. Well, that guy right there could be H2, F2, Cl2, Br2, I2. Any deadly 7 that's single bonded, we're going to say it's H2. So that's one molecule of hydrogen gas. Here's another molecule of hydrogen gas, okay? Now the bond, the nonpolar covalent bond that holds those two H's together is an intramolecular bond or an intramolecular force. And if we took these two separate H2s and somehow got them to stick together, that would be an intermolecular force. Well, these two guys have no reason to stick together, right? There's two H's there, nobody's missing any electrons, so why would they stick together? Well, they would stick together through these very weak London dispersion forces. How could we make them stick together? Pressure. What do you mean pressure? Let's say I have like a propane tank. Doesn't that kind of look like a propane tank? And I put these two guys in there, and I keep putting more and more and more hydrogen gas in there and more pressure until we literally force these two things that don't like each other to stick together, okay? And I'll draw you a picture of that in a second. And then a second later, after we force them to stick together with all this tremendous pressure, right? We're squeezing them. Then we open the tank. The second this tank is open and they come out, then boop, they split apart and go away as a gas again, okay? Well, that's how London dispersion forces work. Well, what is a London dispersion force? I'm about to show you. Here's a London dispersion force. These guys have electrons going around them, right? They have electrons, okay? And then when we push them close together, the electrons literally move away because the electrons are repelling each other. The electrons are actually dispersed and move out of the way because negative charges repel each other. Once the electrons move out of the way enough, then they can gain access to the positive on the other molecule. And we can actually get these guys to just barely stick together through this super, super weak force. This force is so weak that it's like 1/1,000,000th the strength of a covalent bond. And as soon as there's no pressure, boom, they go back apart again, and then they're happily floating around as hydrogen gas. So the dispersion we're talking about is the dispersion of electrons. The electrons are forced to move out of the way because the pressure is so great that we force them to do that. The second type of intermolecular bond is called a dipole-dipole bond. Let's build something we can hook up with a dipole-dipole bond. How about we build a couple of trigonal pyramidal guys? We're going to call these guys, how about NF3? Each of those we're going to call them NF3. So if we drew them like this, on paper, we could say nitrogen trifluoride, right? And of course, I need my unbound pairs on those F's. Okay, and there's one unbound pair right there. So this molecule as a whole is polar. You know that this shape is polar. It's a polar shape, okay? It's got two different ends. It's got this end with the nitrogen on it, and it's got another end with all of the fluorines on it, right? It's polar. Okay, so we have a polar molecule, but not only is it polar in shape, it's polar in electronegativity. This end right here will be the negative end, and this end would be the positive end. Okay, fluorines are very, very electronegative, more electronegative than nitrogen. So if I got some of these guys, I got two of these guys to stick together, how do you think they'd stick together? Well, they flip around and they stick the two different sides together. See, remember, this is the negative side and this top is the positive side. So the negative side of one will stick to the positive side of the other, just like that. Now these guys sticking together, that is a dipole force. In other words, dipole means two different forces. It means two different ends. So the two different ends of the molecule stick together. If there was another one, it would be right there, right? Maybe another one could be right there. So they all line up and they just stick together by their opposite ends. That's a dipole. It's just like magnets sticking together. Dipole is really easy to explain, and it would be easy to draw. I could draw you that again. I could say NF3, and then if we had another NF3, maybe it would be up here. And that's how they'd stick together. The negative end of one would stick to the positive end of another. What if I had another one over here like this? Right? So these guys just flip around and they basically stick to each other like magnets. That's dipole forces. And there's one more, the strongest one, hydrogen bonding. And this is how water is held together. Now there's an expression you need to remember, and it is hydrogen just wants to have fun. It's just like girls. It just wants to have fun. Except if we spell fun, F-O-N. What does that mean? It means that a hydrogen on one atom, if it sticks in a dipole situation to a fluorine, an oxygen, or a nitrogen on another atom, then you're going to end up with a hydrogen bonded substances. I'm going to make one for you. Who do you think those guys could be? These guys are a bent molecule, something, 2, and there's something that's 1. How about H2O? Couldn't those be H2O? 2 H's and an O, right? So let's draw these guys. Well, first of all, we've got 2 H's and an O, 2 H's and an O. I wonder which would be the positive end. Which is the more electronegative, hydrogen or oxygen? Oxygen, okay. So if I drew this molecule right here, I could say H, OH, right? And there would be some leftover unbound pairs there. Now, if another water molecule stuck to that, this is where it would stick together. The hydrogen on one would stick to the oxygen on the other. So hydrogen, if it sticks to a fluorine, an oxygen, or a nitrogen on another molecule, then these two molecules will be held together very strongly. This is a very strong bond. And water is indeed hydrogen bonded. I can show you one more example. Now I've made some more trigonal pyramids. And this time these trigonal pyramids are representing pH3, or phosphorus trihydride. Let's try to draw one of those. pH3, P, H, 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 right? We got an unbound pair. And here's another one, right? Got an unbound pair. These right here, where these two guys stick together, that's an H to a P. Is that a hydrogen bond? Nope. Because this hydrogen needs to stick to an F, an O, or an N on another atom. So what if these guys right here were NH3 instead of pH3? What if we drew them as NH3, right? And I had another one up here. Now, if it's NH3, then these two guys are sticking together right here, an H to an N. Yes, that is a hydrogen bond, because hydrogen on this atom is sticking to an N on the other atom. So these two guys will be stuck together. These two guys will be stuck together much more strongly if it was NH3 instead of PH3. NH3 is indeed a hydrogen bond. If it was PH3, if these exact same molecules, shapes, were PH3, then that would just be dipole-dipole. Because for it to be a hydrogen bond, it has to have FON. The hydrogen has to be with an F, an O, or an N. So no, this one is not a hydrogen bond. And yes, NH3 is a hydrogen bond. Peace out.